Every single day, we're sending texts, we're streaming videos, we're browsing the web, we are just swimming in a sea of information. But have you ever stopped to ask what information actually is? Because it's not just data. It's something way more fundamental and, honestly, pretty surprising. And the answer, well, it's going to change the way you think about every single thing you do online.
So, to get to the bottom of this, let's start with a really simple question that seems like it should have a simple answer. If you want to send the letter A over a wire, how do you do it? As we're about to find out, this seemingly basic problem unlocks a completely new way of thinking about communication.
All right, so this brings us to what we can call the alphabet problem. It's the very first hurdle anyone building a communication system has to deal with, and the most obvious solution is actually a trap. So the intuitive idea is this, right? We've got 26 letters, so let's just create 26 unique signals. Maybe we use 1 volt for A, 2 volts for B, 3 for C, and, all the way up to 26 volts for Z. Simple. One signal for one letter. It seems to make perfect sense. But in the real world, this really elegant idea just completely falls apart. Here's exactly why that simple method is a total no-go. First off, the physical wire itself might not even be able to handle 26 distinct stable voltage levels. It would also be incredibly slow and would eat up a huge amount of bandwidth. And can you just imagine a processor trying to perfectly distinguish between, say, 24 volts and 25 volts with zero errors millions of times a second? So to avoid all that complexity, the unstable signals, the slow speeds, the errors, engineers landed on the simplest possible signal you can imagine, binary. Instead of 26 different levels, we just need 2. On or off, 1 or 0. It's the ultimate solution to the alphabet problem.
Okay, so to understand why binary is so powerful, we have to completely change our definition of information. Turns out it's not about the symbols themselves. It's about probability and, believe it or not, surprise. This quote, this right here, gets to the absolute heart of information theory. The less you expect something to happen, the more information you gain when it does. I mean, think about it. If I tell you the sun will rise tomorrow, have I really told you anything? No, of course not. You already knew that. But if I told you it wouldn't rise, well, now that would be a massive amount of information. The perfect real-world example of this is the lottery. There are millions and millions of possible winning numbers. So me telling you that the number 5 is not the winning number is almost useless information. It was incredibly likely to be true anyway, right? But if I can tell you the one single number that will win, a crazy low probability event, I've just given you extremely valuable information. And this leads to a pretty fascinating conclusion. If the probability of a message is 1, meaning it is an absolute 100% certainty, it carries exactly 0 information. You haven't learned anything new. Information lives entirely in the realm of the unexpected. And yeah, of course there's math to describe this, but don't worry, you don't need to memorize this formula. Just look at what it's saying. Information, I, is related to 1 over the probability p. This just confirms what we saw with the lottery example. As that probability p on the bottom gets smaller and smaller, the amount of information, I, gets bigger and bigger. So if information is all about surprise, how do we measure the potential for surprise in any given system? How do we measure uncertainty itself? Well, that's where a really powerful concept called entropy comes in. Entropy is basically a number that tells you how unpredictable a system is. A system with high entropy is really chaotic and hard to predict, which means any message you get from it is packed with potential information. A low entropy system, on the other hand, is predictable and, well, a little boring. This graph visualizes entropy perfectly. You see that horizontal axis on the bottom? That's probability, going from 0, or impossible, all the way to 1, or certain. The vertical axis is entropy, our measure of uncertainty. Now, just follow that curve. Where does it peak? Bam! Right in the middle. That peak happens at a probability of 0.5, or 1/2. And what event has a perfect 0.5 probability? A fair coin flip. It's the absolute point of maximum uncertainty, because you have absolutely no idea if it will land on heads or tails. Any other probability, like a loaded coin that lands on heads 90% of the time, has lower entropy, because, well, it's just more predictable. Okay, so this is all really fascinating theory. But why does it matter? How does understanding surprise and entropy help us send the letter A more efficiently? This is where we finally put all this theory to work.
Before any message gets sent, it goes through a multi-step digital assembly line. We're going to zoom in on one supercritical step right near the beginning, source coding. This is the stage where all that mind-bending theory about surprise gets put to practical, everyday use. Source coding is really just what we often call data compression. It's the magic step. It uses the probability of different symbols to make the entire message shorter. I mean, in English, letters like E and T are super common, right? But Z and Q are pretty rare. So why would we use the same amount of data for both? That would be crazy. Source coding is smart. It assigns shorter codes to the common letters and longer codes to the rare ones, making the whole message way more efficient.
But this reveals a fundamental trade-off that's happening at the heart of all communication. On one hand, you've got data compression, which is all about reducing redundancy to be efficient. But on the other hand, you have something called error coding, which does the exact opposite. It increases redundancy by adding extra bits so that if there's a little glitch in the transmission, the message can actually be fixed. It's this constant tug-of-war between speed and reliability. So the next time you stream a movie or send a photo, think about what's really happening under the hood. The system isn't just blindly sending data. It's analyzing it, measuring its predictability, and then encoding its surprise as efficiently as possible. It really makes you wonder, doesn't it? How much of our digital world is built not on what we say, but on how unlikely we were to say it.